Hey y'all, welcome back. We are still working with separable differential equations, although today we are focusing in on word problems and really just applications of these separable differential equations. So we've got several word problems here where we're going to want to set up a differential equation and then find the particular solution and answer, usually answer some questions about it. So number one says a car is bought for $36,000. Its value is depreciating at a rate proportional to the present value K. So first of all, it's depreciating, meaning it's losing value. Okay, so let's just make a quick note of that it's losing value. And it says the rate is proportional. So at a rate, the rate here, that's our derivative. That's going to be our dv dt. In other words, the derivative of the value with respect to time. It says it's proportional to the present value. So proportional basically means that we're going to have some kind of scale factor, some multiplier relating the v, the value, to the derivative of the value or the rate of change of the value with respect to time. So we'll call that proportionality constant K, and the present value is V. So yeah, that's your V, is the value. So after 2 years, the vehicle is worth $18,000. So this will come into play later, but let's make a note right here that we've got two coordinates that we're going to use to both find C, the constant that we'll get after we integrate, that constant of integration, but we're also going to have to figure out what that proportionality constant is. So it says that a car is bought for $36,000. That's the initial value. So after 0 years, it's worth $36,000. However, after 2 years, it's worth $18,000. So we've got this other implied coordinate here, 2, 18,000. Okay, so part A wants us to write the differential equation to represent the scenario here. So the rate at which the value is changing with respect to time is proportional to the value itself. And so we want to come up with an actual function for V here. That is the differential equation. So that is our answer for part A. But in order to find the value of the car in 5 years, we are going to have to find a solution to that differential equation. In other words, we're going to have to figure out a formula for V. So to do that, we are going to separate the variables like we did in class and like we've been doing with all these separable differential equations. We're going to divide both sides by V to get 1 over V, or V to the negative 1, dV equals K dt. Now, K here is a constant, so imagine it's like 2 or something like that. And if we're going to integrate that with respect to t, then, let's say we wanted to integrate something like 5 with respect to x, right? If we integrate this, we get 5x because 5 is the slope of 5x. Of course, we'd have a plus c on there. But this is going to work basically the same way, except it's in terms of t instead of in terms of x. So maybe I'm getting a little ahead of myself. Let's integrate the left-hand side. This is going to be one of those integrals that you have to know, which is that the integral of 1 over x, or x to the negative 1, is the natural log of the absolute value of x. So here we've got the natural log of the absolute value of v equals kt plus c. Now, solving for v, we're going to get a function that's very similar to what we had in the notes, which is that a equals pert equation, but just with different variables here. But let's show the algebra to see how we get there. So we're going to exponentiate both sides. Absolute value of v is going to be e to the kt plus c. But I'm going to do a little algebraic manipulation on the right-hand side, kind of simplify that a little bit. We also know that the value here can't really be negative, so it doesn't make sense to have a negative v value. So when we go to get rid of those absolute values, and then normally we'd put the plus or minus on the e, we can see that all the values that are given are positive. So we'll just go ahead and say v equals positive e to the kt times e to the c. And if you don't see how I did that, let me remind you of a little exponent property here that says a to the x times a to the y. Whenever you multiply two powers with the same base, you add those exponents. So you could take that backwards. In other words, if you've got a sum in your exponent, you can split that up like this, okay, which is exactly what we're doing here. Now, the reason for doing that is because e to the c is just some other constant, right? So this term right here is just a constant itself. Euler's number is a constant. When you raise a constant to a constant, you get another constant. So we're just going to call that new constant c. I know it's a little uncomfortable because it's not the same as the c value that we had before, but at the end of the day, we're just trying to come up with a value for v, or a function rather for v, and we're going to need that c anyway. So we're going to write this as v equals c, which is that new constant, that's the e to the c that we got here, times e to the kt. And that's going to be sort of our generic function for, anytime we've got a proportional rate, it's just really describing an exponential function. So we've got a few different things that we need to fill in here. And actually, let me move all this over so I can kind of work left to right here. So let's go ahead and find the c. Now, as we talked about in class, if the equation gets set up like this c value is always going to be the initial value. So if you can remember that, we can see that the initial value is 36,000. That is going to be the c. But if you don't remember that, that's okay. We can still find c by substituting in 0, 36,000. Right? We'll have 36,000 equals c times e to the k times 0. Anything to the 0th power is going to be 1. And so you can see algebraically why c definitely has to be that 36,000. So notice that is the initial value here. So let's go ahead and rewrite our equation now. V equals 36,000 times e to the kt. And now we need to find the k. And we can use the other given point, 2, 18,000, that other given information to figure out k. So if the value is 18,000, and now we know what the c is, it's 36,000, times e to the k times 2, because it was after 2 years the value was 18,000. Now if I divide both sides by 36,000 here, I'm going to get 1/2. So I have 1/2 equals e to the 2k. And then to isolate that exponent, I need to take the natural log of both sides. So I have the natural log of, maybe I'll just rewrite this at 0.5 just because the fractions are getting a little, they're just kind of taking up a little bit more space than I'd like, equals 2k here. And then I'll divide both sides by 2. So k is half of natural log of 0.5. I guess I'm kind of mixing up decimals and fractions here, so maybe I should stay consistent. Maybe I will go ahead and just stay with that fraction. Okay, so that's my k value. Now I can write like my final or my particular solution to that differential equation. V equals 36,000 times e to the power of half natural log of half times t. Now to find the value at 5 years, clearly we're going to need a calculator for this. Everything else you can do pretty much without a calculator, but this last computation we are going to have to estimate with the calculator. I'm just going to work that out over to the side because you don't really need like a specific Desmos or anything. You can even just use a basic scientific calculator for this. So 36,000 times e to the half times the natural log of 0.5 times, we want after 5 years. So basically I didn't really write that, but we wanted to substitute in 5 for t. Okay, so maybe I'll just make this a little bit more clear. When t is 5, v is approximately $6,363.96. And I got that from the calculator. I did not calculate that in my head, obviously. Okay, so there you go. You got the value of the car after 5 years. Number 2 says the amount of radioactive substance decays according to the equation dy dt equals ky, where k is a constant and t is measured in days. If half the amount present will decay in 20 days, what is the value of k? So we have basically the same kind of setup here. Let's go ahead and isolate. Let's solve for y. So we have a function y in terms of t. This is actually going to work out exactly the same as the previous problem. You can see that the setup is basically exactly the same. So I'm going to work through this pretty quickly. Okay, I'm not going to try to narrate every single little step here. I'm just going to go through it real quick because you are going to end up in the same place. And there we go. So that's our equation for y. Now we're going to have to do what we did before and find the c, find the k. Okay, so it says half the amount is present. If half of the amount present will decay in 20 days, what is the value of k? So we have some initial amount, which is the c, and we want to know if half of that amount is present after 20 days, what's the value of k? So whatever the initial amount, remember this is the initial amount, okay, and whatever the t value is, in this case it'd be 20 for 20 days, we want the final amount, the y, to be 20. So we'll say 20 equals, oh, I'm sorry, no, the final amount's not 20, sorry, that's the number of days. The final amount is half of the initial amount. So we'll just say half of c is equal to c times e to the kt, in this case 20. And we're going to isolate k here. So we can actually divide both sides by c here and get 1/2 equals e to the 20k. Now we can take the natural log of both sides, get the natural log of 1/2 equals 20k. So k should be natural log of 1/2 divided by 20. This is going to be something I'll type into the calculator. So I'm going to do that off to the side here. Natural log of 0.5 divided by 20. So k is approximately negative 0.034, which I'd be happy with on a free response question, but all these answer choices are going to be rounded, so we're just going to call that a 5. Okay, so our answer is D. Number 3 wants us to evaluate these integrals. So this is just going to be kind of a throwback to what we did right before spring break, and that is we're just going to practice our u substitution skills here. So on the first one, we're going to let u be x to the 5th plus 5. So du would be then 5x to the 4th dx, and look at that, we've got a perfect match there. We've got the 5x to the 4th and the dx. So we can go ahead and write this as the integral of 1 over u, that's u to the negative 1, du. Now we've done so many of these at this point that I really hope that you can integrate that without any trouble at all. It's going to be the natural log of the absolute value of u plus c. And since we determined that u was x to the 5th plus 7, we can write this as the natural log of the absolute value of x to the 5th plus 7. That should be an absolute value bar plus c. For letter B, and this one might not be as obvious, but we can let u be 2x plus 3, and therefore du would be just 2 dx. Now here we do not have a perfect match, so I do need to divide both sides by 2. 1/2 du is dx, and now I can make my substitutions. So this will equal the integral of u to the 7th times 1/2 du. Don't forget that you can put that 1/2 on the outside and make that integration a little bit easier. So here we're just going to use the anti-power rule and increase that power by 1 and then divide by that new power. So 1/2 times 1/8 is 1/16. And actually, I'm going to switch back over to red here because we are ready to plug back in our x's. So 1/16 times 2x plus 3 to the 8th plus c. And now letter C is going to be the last of this little trio of u substitution problems. We'll let u be x squared minus 8. So du would be 2x dx. Here, again, I do not have a perfect match here, so I need to modify that 2 to make it become a 5. Okay, so I needed to first divide both sides by 2, and then multiply both sides by 5. So 5 halves du is 5x dx. So this integral will equal the integral of the square root of u. So it's really going to be like, maybe I should write that as u to the 1/2, and then times 1/2, or 5 halves, du. So this will equal 5 halves, and then we can use the power rule on this one, or the anti-power rule. U to the 3 halves, and then I need to divide by 3 halves, which would be the same thing as multiplying by 2/3. Now the 2's here will reduce. 2 over 2 is just 1. So I get 5/3 u to the 3 halves plus c. So my final answer here is going to be, I'm going to switch back over to red now that I'm ready to plug back in my x's. 5/3 times x squared minus 8 to the 3 halves plus c. Kind of fix that box so we can clearly read the answer. That looks a little better there. Okay, number 4, looks like we are working with a slope field. We've got a differential equation that is x plus 1 over y. That means that's going to be our slope, or dy dx. That is giving us the slope of the function. So it says on the axes provided, sketch a slope field for the given differential equations at the 12 points indicated. Okay, so here's the thing, is you really want to be able to kind of do all this in your head. The calculation should not be too bad. I'll kind of maybe show 1 or 2 of them, but hopefully you can kind of get the pattern going as we move forward. But let's start with -1, 2. That's that top left point. To do this, we're going to substitute in -1 into x. So we get -1 plus 1 over 2, which is just 0. Okay. So a slope of 0 is horizontal, so I'm just going to draw a little horizontal line here. And then as I'm looking at that, I'm noticing that when x is -1, that numerator is always going to be 0. So when x is -1, the slope should always be 0 here. So I'm just going to draw these horizontal lines all the way down. Now, here's something else that's kind of weird, is that when y is 0, when the denominator is 0, the slope is going to be undefined. So I've got undefined slopes going like this. Now, what is happening here? Is it actually 0 or is it actually undefined? And because it can't be both, it's either going to be undefined or defined. And because you have that divide by 0 error, this is actually going to be a vertical slope there. Okay, now let's move on to when x is 0. So when x is 0, let's just start at the top here, 0, 2, and plug in 0. I get 0 plus 1 over the y value, which is 2. So that's going to be 1/2. And to just kind of generalize what's going to happen when x is 0, the numerator will always be 1. So we really just are going to have like 1 over whatever the y value is. So like when y is 1 here, we'll have 1 over 1, which is 1. So I have like this, kind of 45-degree angled slope. We're going up 1 over 1. When y is -1 and x is 0, I'll have 1 over -1. So this slope is going to be -1. When y is -2, I'm going to have -1/2. So it's going to be like not quite as steep as this -1, but still angled downward. Now, when x is 1, we'll just do 1 point to just kind of show you what's going to happen here at 1, 1. 1, 2. We're going to have 1 plus 1 over 2. That's 2 divided by 2 is 1. Okay, yeah, my slopes aren't really looking that great here. I'm trying to get it to look good, but okay. So when the x is 1, that numerator is always going to be 2. So it's going to be 2 divided by the y value. So 2 divided by 1 is 2. That should be a little bit more sloped. 2 divided by -1 is -2. So that's going to be going down like this. And 2 divided by -2 is going to be -1. Okay, so you almost like what I'm seeing here. It's kind of hard to tell, but it's almost looking like it's going to do this. But yeah, I guess we got to find out exactly what that function is going to be. And that's what we're going to do in part B. It says find the particular solution given the initial condition that 0 is -2. So we got the slope from before, but we'll use that initial condition to find the c value. So let's go back to that original dy dx, which is x plus 1 over y. We're going to solve this for y using the separation of variables technique. First, I'll multiply both sides by y to get y dy, and then move the dx over in a similar way. Now, neither one of these sides are composites, so when I integrate both sides, I don't have to worry about doing a u substitution. I can just use the good old power rule. So on the left side, we'll have 1/2 y squared, and on the right side, we'll have 1/2 x squared plus x, and then we'll include the plus c over on the right-hand side. Next, I'll multiply both sides by 2 to get y squared equals x squared plus 2x plus really 2c, but we're going to combine that kind of like we did earlier with the e to the c. We do have to know that these two c's are different. They're not the same c, so what I would suggest is maybe not using that previous equation to solve for c, but rather use this one. So we'll come back to this one to get c. Lastly, I'm going to take the square root of both sides. So I get y equals plus minus the square root of x squared plus 2x plus c. I do need to decide whether or not it's going to be plus or minus, and I can make that decision based on the initial condition that f of 0 is -2, meaning that at least one of the outputs has got to be negative, which means they all have to be negative. So all these should have the same sign because the square root of whatever, always gives you a positive number. So we're going to disregard this plus and keep the minus there. And now we're ready to go find c. We'll use the initial condition that f of 0 equals -2 and plug in -2 into y and 0 into x. This should simplify pretty nicely. We get 4 is c. So here we go. We're ready to write the actual equation here. Final answer, y equals negative square root of x squared plus 2x plus 4. Okay, yeah, let's move on to number 5. This is going to be a very similar problem here. So we'll go ahead and start calculating some slopes. We do want to be looking for patterns so that we don't have to spend too much time just doing a bunch of computations. Again, dy dx, that's the slope. And so let's see if we can't start with some zeros here. Let's see if we can't zero out anything. Like for instance, when x is 0, the slope has got to be 0 because 0 times anything is 0. So wherever x is 0, regardless of what y is, the slope will be 0. So here, 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 and here, that's always going to be 0. Now, if y is 1, then this factor will be 0, meaning the whole slope would be 0. So when y is 1, dy dx is 0. So we'll go to y is 1 and plot those horizontal lines as well. Now, we will have to do some computations here to get the rest of the points, but I like to get the easy ones out of the way first. So, yeah, let's start with -1, 3. So at -1, 3, if I plug that in, I'm going to get -1 squared is 1 times 3 minus 1 is 2. 1 times 2 is 2. So a little bit more than that, 45 degrees. A little steeper than a slope equals 1. Now, if I plug in -1, 2, I'm going to have 1 times 2 minus 1. 1 times 2 minus 1 would be 1 times 1, which is 1. So yeah, this equals 1. And finally, negative 1 comma 0 is going to be 1 times negative 2. Oh, wait a minute. Sorry, no. Negative 1 minus 1. Oh, no, that is right. Oh, hold on. Let me think for a sec. We're plugging in 0. Sorry. So, yeah, negative 1 squared is 1 times negative 1 is negative 1. And now let's move over to the right-hand piece of this where x is 1. So at 1 comma 3, we have 1 times 2 is 2. At 1 comma 2, we're going to have 1 times 1 is 1. And at, let's see here, 1 comma 0, we have 1 times negative 1 is negative 1. Now, I was a little sloppy with my notation here, kind of looking back at what I wrote. I really should be saying that, when, at this point, this is the slope. And I didn't really communicate that very well. Like this point doesn't equal that. So let me erase those equal signs. It's not really, maybe I should do a colon just to make it clear that, hey, I'm not saying these things are equal. I'm just saying at that point, we have the given slope. All right, so yeah, your slope field should have looked something like that. Part B says find the particular solution given that f of 0 is 3. So we'll solve this just like the last one. Start with that dy dx equals x squared times y minus 1. Then we'll divide both sides by y minus 1, and we see, hopefully you see that we are going to have to do a u substitution on that one, but luckily not on the right-hand side. So when we set up that u substitution, we're going to have to integrate both these sides. I think what I'll do is just do the u substitution over to the right. If u is y minus 1, then du is dy. And I forgot to write the dy. Let's go back and throw that in. And yeah, actually we get a perfect match here, which is kind of nice. So the integral of u to the negative 1 du is going to be the natural log of u plus c. All right, so that integral will be the natural log of the absolute value of y minus 1 equals 1/3 times x cubed plus c. All right, so we need to raise both sides to the power e. And so this is probably going to be the one that we want to use to actually solve for c when we're ready to come back to that, because everything else I do not think is going to affect that c individually. So yeah, raising both sides to the power of e, we get absolute value of y minus 1 equals e to the 1/3 x cubed plus c. We can get rid of those absolute values by doing plus or minus. And since we have an output of a positive number here, we know that we're going to take the plus. So y minus 1 equals positive e to the 1/3 x cubed plus c. And then adding 1 to both sides, we get y equals e to the 1/3 x cubed plus c plus 1. All right, so now we're going to go find that c. Just make sure we're clear about what happened here. I'm just going to put a little arrow here, kind of explain where that work goes. Okay, so yeah, we're going to plug in 0, 3 here. We've got the natural log of 3 minus 1, so natural log of absolute value of 2, which of course we know is just going to be 2. 1/3 times 0 cubed plus c. So the absolute value of 2 is just 2, so we get natural log of 2 equals c. So c is the natural log of 2, which means we can go and rewrite this equation now as y equals e to the 1/3 x cubed plus natural log of 2, although we've seen that, or we've at least talked about, when you get an equation in this form, you want to be ready to rewrite this whole power natural log of 2 here as a coefficient. So, doing kind of like we did back up, where did we do that? Oh yeah, here, where we move this to be that coefficient. Kind of like that, a little different here because we're not dealing with a constant here. Oh, it is a constant, but e to the natural log of 2 is just 2. So that answer that we have there is fine, but what I think you're going to see on a multiple choice question is we're going to have 2 times e to the 1/3 x cubed, and then of course that plus 1. There you go. There's your particular solution. That is a pretty wild function there. I'm really curious to see what that would look like in a graphing calculator. Okay, number 6, we're matching differential equations with the appropriate slope fields. So here we're just going to kind of see if there's anything we can, narrow down here, and see if we can't figure out what is going on. So the first thing I'm looking at is letter choice A, and I see that when y is 2, dy dx is 0, right? So let's see if we can't eliminate any answer choices there. Yeah, maybe we can't. Not really seeing. Oh, you know what? Yeah, we can. Right here, boom. I think this is going to be our answer. It's going to be A. 2 minus 2 is 0. That was pretty easy. Yeah, so let's take a look at B. What's going on with B? Well, in B, when x is 0, the slope is 0. So let's see here. That could be this last one. Sine of 0 is 0, so it might be this one. We'll come back there. So yeah, it's either going to be one of these two, but I think you'll see it real quickly that C is going to be this sine function. I mean, look and see, like, what's going on here is we've got, like, if you try to follow these slopes and see, you kind of get something that looks like this, yeah, which is our negative cosine function. And the derivative of negative cosine is positive sine. So yeah, for sure that one's going to be C, which means B is this last one. And just to take a quick look at D, like if we pick a point, like say, like 1 comma 0, this point right here, 1 minus 0 is 1, and we can see we've got that slope of 1. And that's going to be true for all these like diagonal slopes here. The slope is 1, and that's going to happen at 1 comma 0, at 2 comma 1, at 3 comma 1, and we're seeing like all those work with this last equation, right? 1 minus 0 is 1, 2 minus 1 is 1, 3 minus 2 is 1, etc., etc. So there you go. That one's D. Uh-oh, we're blank. Give me a second for this to load. And we're back with some more slope fields. All right, I know you guys love these slope fields. Okay, now letter C, is that just the same one we did before? I think that letter C, I recognize that one. Oh yeah, we just basically solved that one. We don't need to really do it again, but yeah, we can see that's going to be this one right here. Same kind of reasoning goes here. 1 comma 0 right here. 1 minus 0 is 1. 2 minus 1 is 1. 3 minus 2 is 1, and etc. Are any of these other ones the same? No, just that one kind of got mixed in there. Okay, so let's look at some of these other ones that maybe not so obvious. Now I'm looking at what kind of catches my eye on B is, and that's really, you just want to kind of look for some patterns, some, plug in some points. And I think between those two strategies, you can figure out most of these. So here we see that when x is 2, the slope is 0. So let's see, is that going to be true for, yeah, I'm not, so for sure it can't be this one, right? Because when x is 2, we get 1 plus 1 is 2. So yeah, it's definitely not that one. It might be this one. It might even be this one too. Actually, no, I don't think it's that one either. I think it's going to have to be this one. But let's see if we can't find anything else that can help us here. Oh, wait a minute. Wait 1 minute. Yeah, I was getting a little confused there, but you probably already saw my mistake here. Probably yelling at me through the computer screen or your phone. This should be negative 2. Oh my goodness. Yeah, so when x is -2, the slope is 0. Yeah, so this one, then it becomes a lot more clear here. Yikes. Okay, yeah, this one's got to be b, because 1/2 times -2 is 1, or -1, and -1 plus 1 is 0. So for sure that one's going to be b. Okay, so we've got b, we got c. So now we're just looking at a and d. I'm going to start with d, I think, because it looks like we've got a bunch of zero slopes when y is 0. So if y is 0, then the slope is 0. And yeah, that's got to be right here. Finally, just to kind of make sense of A, notice it's looking like we got a bunch of circles here. This is one that we've actually found. This was actually the very first implicitly defined equation that we differentiated way back last semester, and actually was the first one we integrated back on day one of this separable differential equations. I think so. That would have been like, no, what day are we on? We're on 7/6. So that would have been like 7/3. So yeah, day one we went over how to find the equation that represents the slope of x squared plus y squared equals 1, and it was certainly this. So you could plug in a few more points if you're just like not totally convinced that that's going to be the answer. I mean, process of elimination kind of gives it to us, but let's just pick a point here. Like let's say we pick 1, 1. We can see we've got a slope of -1, and that definitely checks out there. Okay, number 8. Is that? I guess that's it. Number 8. So number 8, it says find the particular solution for each of the following differential equations. So we're just going to solve these like we normally would. We're going to separate the variables, integrate, solve for y, solve for c. You guys know the drill at this point. Y prime I'm going to rewrite as dy dx just to make the algebra look a little nicer. Then I'm going to cross multiply here to separate the variables. So I get y dy equals 5x squared dx. Next, I want to integrate both sides. And I'll get 1/2 y squared equals, what would that be? 5/3 x cubed. And yeah, I need to multiply, plus c, of course. Come on. Now we're going to multiply both sides by 2. So I'm going to get 10/3 x cubed plus c. And now that I'm done changing the c, because the c did change here, because it will be twice as much. But now that I'm done changing the c by itself, I know I'm going to use this to find my c, this equation right here. So last thing is we need to take the square root of both sides. Square root of y squared is absolute value of y. So we know we're going to end up with a plus minus here. Plus minus the square root of 10/3 x cubed plus c. And since our output of this 1 is positive, we are going to choose the positive and disregard the negative sign there. So now let's find the c. We're going to plug in 1. So we've got 1 squared equals 10/3 times 1 plus c. So we've got 1 minus 10/3 is c. 1 is 3/3. Just doing a little fraction action here. And so we get -7/3 is c. So y is going to be the square root of 10/3 x cubed minus 7/3. Not too bad. Yeah, no u substitution or anything necessary on that one. Letter B, our last problem for tonight. We've got dy dx equals 3 times root x times y. So we're going to divide both sides by y, giving me y to the -1. dy equals 3 root x dx. Now we're going to integrate both sides. Which will give me the natural log of the absolute value of y equals, now hang on here, 3 root x is really like 3 times x to the 1/2. So I have 3 times x to the 3/2, right? 1/2 plus 1 is 3/2. And then I need to divide by 3/2, which would be equivalent to multiplying by 2/3. And this one actually simplifies pretty nicely. 3 times 2/3 is just going to be 2. So let's go ahead and just maybe do that one little simplification here. And now I want to get rid of the natural log, so I'll exponentiate both sides. I guess well, yeah, I'll just keep rolling with it. Um, Here we want to get rid of the absolute value, so we need to decide plus or minus, and we're going to do plus again because our output is positive here. So y is equal to e to the 2x 3 halves plus c. And so now I'm going to use the coordinate 0, 4, and I'm actually just going to go ahead and use this last problem, this last equation here to get it. I think we'll be okay here. There's not really, you know what? No, I'm thinking we're going to have to go back and resolve that for y anyway. So let's take this back a second. Oh, you know what we could do? I just realized something. We could actually, no, I am going to go ahead and go back. Sorry. I'm going back and forth. I'm being indecisive. I'm going to go back to this one right here to find the c. So let me just maybe show that down here. We've got the natural log of the absolute value of 4 equals 2 times, not x there because we're plugging in 0 here, 0 to the 3 halves plus c. Now 0 times anything 0, so c is going to be the natural log of 4. All right, now going back to this equation here and plugging in that c, we get y equals e to the 2x to the 3 halves plus natural log of 4, which we can simplify a little bit more. Using those exponent properties, we can split this up, and e to the natural log of 4 is just 4. So our final answer here should be 4 times e to the power of 2 times x to the 3 halves. And that's going to wrap it up for tonight. As always, please let me know if you have any questions or you want me to go over any of these problems in more detail. I'd be happy to help you out. Thanks for watching. Y'all have a great day.